There's a revolution happening in medicine right now. But it's not what you think. It's not taking place in a lab or an operating room. It's happening on silicon. And the whole thing kicks off with just one number. So what is this number? 200 gigabytes. That, right there, is the sheer amount of raw data you get from sequencing just one person's genome. Think about that. And remember, that's just your genes. Now, what happens when we start piling on more? I'm talking decades of your health records, the nonstop data stream from your watch, plus super deep analysis of your body's proteins. Suddenly, you're looking at the new complete profile for every single patient. It's massive. So that's the big question, isn't it? That's what we're really digging into here. When every single patient is basically a walking, talking data set, how on earth can medicine possibly keep up with this data tsunami? All right, let's break this down. First up, that tsunami of medical data. You see, the problem isn't just that it's big. I mean, it is. But the real kicker is how fast it's growing. We're talking bigger every single second. Okay, let's put some real numbers to this so you can feel it. A single 3D MRI, that's like half a gig. A high-res CT scan, boom, a full gigabyte. That digital slide from a biopsy, we're talking several gigabytes. And a full-body scan, you're easily into terabytes of data. This isn't some sci-fi movie, folks. This is just another Tuesday in a modern hospital. So, how do we even begin to make sense of this data flood? Well, the only real answer is AI. But, and this is a big but, that solution brings its own huge problem to the table. These AI models, they're not just big, they're hungry. They have this bottomless appetite for computational power. And this is where you can really see the AI arms race in action. I mean, look at this. Not long ago, we were dealing with models that had maybe 25 million parameters. Today, we're talking vision transformers with a billion. The next step is multimodal models that chew on images, text, and genomics, and they'll have over 10 billion parameters. And what's on the horizon? People are talking about foundation models for medicine with over 1 trillion parameters. The scale is just mind-boggling. And this isn't just some abstract number on a slide. To train just one of these modern medical AIs, say one that analyzes CT scans, you need somewhere between 40 and 80 gigs of dedicated VRAM. That is a massive hardware ask. Okay, so that brings us to the next big shift. Because here's the thing, it's not just about training these models in some lab anymore. The real game changer and the real challenge is putting them to work in the clinic, in real time, 24/7. And check this out. By 2026, the forecasts are pretty clear. The workload is going to flip. Inference, that's the fancy word for actually using the AI on new data in real time, is going to make up 2/3 of all AI computing. So the heavy lifting isn't building the AI anymore, it's running it day in and day out. And the demands in a clinic are just extreme. I mean, picture this. An AI that's constantly analyzing every new patient scan that comes in around the clock. Or in an operating room, where an AI helping a surgeon has to react in less than 100 milliseconds. And all of this is happening while the hospital system is juggling data for hundreds of other patients at the same time. This is a nonstop life or death workload. So you can probably see where this is going. We're hitting a hardware bottleneck, a big one. All these insane demands are creating what engineers call a memory wall. And the problem is, the tech we've been using, it just can't climb it. Let's make this super concrete. Let's look at the hardware showdown. The last-gen chip, the H100, it had 80 gigs of memory. Pretty good, right? Well, the new B200 has a whopping 192 gigs. And bandwidth, basically how fast you can shovel data into it, has more than doubled, all the way up to 8 terabytes a second. And the most important part? For that real-world, in-the-clinic inference work, the new chip is twice as fast. So why does all that tech speak matter? Well, here's the key takeaway. Modern AI workloads are memory-bound. That means the chip itself is so fast, it spends most of its time just waiting for data to show up. The bottleneck isn't how fast it can think, it's how fast we can feed it. That is the memory wall, and that's exactly what this new hardware is built to smash through. Now, this new hardware is, let's be honest, ridiculously expensive. So why is every hospital and research lab on the planet scrambling to get their hands on it? Simple. The payoff isn't just better medicine, it's the economics.
It's kind of crazy, but spending a fortune on this stuff is actually a huge money saver.
Okay, let's talk drug development. By using AI to make clinical trials smarter, finding the perfect patients, watching results as they happen, a company like Eli Lilly could potentially shave off $25 billion in development costs. That's billion with a B. Or think about a doctor's day-to-day grind. AI can automate all that electronic health record nonsense. We're talking about cutting down a doctor's admin work by a staggering 80%. That frees them up to, actually focus on patients instead of paperwork.
And this isn't just a one-off thing, it scales up. The public health sectors that are already jumping on these advanced AI tools, they're seeing productivity boosts of up to 42% across the board. The gains are real, they're immediate, and you just can't argue with them.
So when you're looking at a return on investment that's this huge and this fast, the whole conversation changes. The decision to upgrade isn't just a clinical one anymore, it's an economic one. At this point, not upgrading is basically financial malpractice. And that brings us to the final and maybe the most important piece of the puzzle. This isn't just about buying a new server every couple of years. No. We're talking about a whole new way of life for the entire medical industry. We're talking about the upgrade treadmill. Think about this for a second. Right now, healthcare has one of the lowest adoption rates for generative AI. We're at just 15%. Now, it's not because they don't want it, it's because of all the safety rules and regulations. But what happens when those hurdles start to come down, which they will? That other 85%, that's not just potential growth, that's a massive tidal wave of demand that's about to hit. So, where does that leave us with this one big idea? As the data keeps exploding, as the AI models get even hungrier, and as the economic pressure becomes impossible to ignore, the entire medical world is facing a new reality. This isn't an upgrade cycle anymore. It's an upgrade treadmill. It's this relentless, nonstop race just to keep up, and if you stand still for even a second, you're going to get left behind. The revolution is absolutely here, and it runs on silicon.